target hardware is Majorana qubits topological quantum computing. I guess just very, very briefly, we observed Majoranas in the lab, I believe it was in 2012, and are actively working on building topological qubits out of them. I've been to the lab in Redmond. We have labs around the world, very interesting, but I'm not here to present that today. Instead, I'm going to go the other direction and talk from the top, namely our software stack, working down. And in particular, I'd like to spend a little bit of time talking about QuArC, which is the Microsoft programming language, quantum programming language, and a little bit about the Quantum Development Kit, QDK. Ooh, tough to get that out this morning. And so let me go ahead and get started. I don't think there's any doubt that we need a quantum programming language. Everybody expects that. But what do we expect to gain out of that? All right, so in fact, yesterday there was a large workshop here about cost estimates for quantum algorithms. Okay, and so a quantum programming language, as its functionality, should be very good at estimating the cost of a program without necessarily being able to run it. And so we have, and I discussed this in detail yesterday, quantum chemistry examples where using QuArC and improving the algorithms and looking at compiling and a number of other tricks have reduced the estimated cost, the cost that you would expect on paper of these algorithms, to go from something that's completely intractable to something that, with reasonable assumptions about gate speed and whatnot, is quite reasonable. So another thing we'd like to expect out of our programming language is to debug it. And this is the thing that keeps me up at night. And I'm not going to spend a lot of time talking about that because I don't think there's a great answer here. Right, so this is what things usually look like when I write code. Sure enough, I have not actually successfully written any type of quantum algorithm correctly on the first try. One could argue that I've never written any algorithm whatsoever correctly on the first try. And so identifying where the problems in a quantum program, where they lie, is one of the most challenging tasks I could imagine. So let me just spend a minute. The most recent example I did is I coded up in QuArC an algorithm to simulate a quantum key distribution protocol that I've been working on with one of my graduate students. And so we wanted to test how robust it was against imperfections in the hardware that we're using to simulate it. So in quantum key distribution, we have an ideal protocol, but we have real hardware that's supposed to implement it. And we'd like to understand, well, the errors in this hardware, how large can they be before, indeed, has a mind of its own, doesn't it? How large can the errors be before the users believe that they're being eavesdropped on and reject the protocol itself? Okay, and so working through gate synthesis, I found several bugs in papers that have described how to do that, and I wouldn't have realized that without simulating it and actually running the simulator and realizing that the statistics that it's predicting doesn't match the statistics of what was in the papers. And so in particular, it wasn't even the statistics of the output, it was the statistics on how many gates should it be using. It was taking branches that it shouldn't have taken, and therefore the gate counts were off. Okay, and so we can actually see that come out of the programming language, that it would be very, very difficult to identify those just looking at the circuit diagrams of how to do the synthesis algorithm. Okay, so third, and that's really what I want to focus on today, is how do we construct algorithms? How do we make applications? What does the programming language do to help you do that? Right, and so there's a lot of choices about how to build a quantum computing language, but I've seen this type of picture everywhere. Everybody seems to have the same notion of what a stack should be, and I'm not going to complain about it because I think it's the right thing. Up there at the top is where we're living with our applications and our programs, and QuArC maybe is perhaps the very top part of that squiggly arrow, which goes down to the control software, living at a cryogenic level, I guess, ideally for a lot of systems, and then further down, that actually drives the computer itself. This picture is really the driving point behind the development of QuArC. The quantum computer down at the bottom is, in some sense, not the computer. The computer is still living up at the top of the applications. The quantum computer is a device that's going to be queried to give us the results of a particular computation out. I think I have a setting incorrectly on PowerPoint. It's a little embarrassing. I should at least know how to use this piece of software, yet alone anything I try to build. And so really I'm going to talk about way up at the top, the quantum development kit, which is what we use to build our applications, and maybe the little top of the squiggly arrow, QuArC, which is the thing that we use to develop those applications. All right, so at the very, very top, we have the development kit. I guess the most recent news on this is if you go to GitHub on GitHub Microsoft Quantum, you will find a number of libraries and samples available for a variety of programs. In our next release, which is scheduled for July, I'm not exactly sure when in July, so it could be like in a week, but more likely closer to a month, we're going to release the entire quantum development kit in open source. And so the whole thing will be available, all the QuArC, not only the libraries, well, everything in QuArC is a library, and so all of it will be available to work with, and of course, we're seeking to have as many of you contribute to it as possible. We want to develop a good community in developing these libraries. Okay, it's already integrated into Visual Studio. We have a Python integration. We have a Jupyter Notebook, although I have to admit myself, I have not successfully run the Jupyter Notebook because I'm incompetent at that kind of stuff. Works on my Macs, which I really like, as well as this Windows device, which I'm having trouble actually operating. All right, it's built off of .NET. That's great if that's the kind of thing you're interested in. I'm really more of a Haskell programmer, and so I have to sort of get back down to C# to write things. It does have support in F#, which is a plus. Simulators, very good. Cost estimator is the thing that I like to use the most. Okay, it's not the fastest thing in the world, but it does a good job in doing exactly what you want. Count the number of gates that you have in your algorithm. Is that really what you think you should have had? All right, as well, documentation. All of the algorithms, everything that you can call in the language has complete documentation on the Microsoft Docs. And so here we see an example of the quantum phase estimation algorithm here, an explanation of what the algorithm is, as well as the appropriate way to use it within QuArC. All right, QuArC itself, high-level programming language, rich libraries. I think the most important bit is there's a lot of classical logic that's interleaved between the quantum operations, and so when you program in QuArC, it's really a hybrid programming environment. You still have the for loops, the branching you would expect out of a classical logic, as well as the quantum operations that you'd like to do. Okay, so in particular, doing things like adaptive measurement, changing the computation based on measurement outcomes, that's done within QuArC itself. It also could be done in terms of measuring, returning it to the driver itself that's, say, written in C# or Python, and then modifying the QuArC code by passing the values appropriately, or done within QuArC itself. All right, so what is the philosophy? Oh, I'm sorry, one last slide. So there's a community being developed. I guess I've already said all of this. It's all available on GitHub, Microsoft.quantum, to find all of the open source contributions now. The entire QDK will be there next month. Plenty of documentation and some links to social media, etc. All right, so this is the effective definition that drove the development of QuArC. This is not my definition, and I'm still on the fence about it personally. Right, so I can certainly understand where it comes from. If we view this full stack view, and the quantum computer itself is a device, then you can think of the programming language more as a device driver. Okay, so you're going to write some code. The code is going to send stuff down to this device, which sort of exists in its own right, and results are going to come back up, maybe heralded, maybe you have to query them. You know, I guess that's to be determined. In which case, we really think of the device as producing side effects in these measurements, but you're just driving a classical program at this application layer. Okay, so that philosophy really dictates how the program is designed. So not only do you have, so within the intrinsic, we have all of the quantum operations that we have here, which is exactly the kind of stuff you'd expect. Inside QuArC, since we also have classical computation that's been built into that, we have these deterministic things that we can use to then drive our loops and drive our branching, etc. But the real interesting part then is that if we're going to treat our system as a device, it doesn't make a lot of difference what that device is. We can target many, many different backends with exactly the same pieces of code. Okay, we don't need to change the code if we're going to do a simulator versus a resource estimator. The code itself just says something happens to the qubit, and the back end will figure out exactly what that is. Okay, so the little dotted line for the quantum hardware is anticipatory, but the simulator and the resource estimator are there right now. I'll show some examples of calling the simulator. Calling the resource estimator is exactly the same code. All right. Great. All right, so that was all very philosophical. Let me actually drive all of this by an example. This is perhaps the simplest example I could imagine. And in fact, this is not terribly dissimilar from what I just mentioned, building a simulation of a QKD protocol. The very first thing you do is you create some entanglement. And this is the preliminary step in that. We're just going to do a Hadamard gate. If we're going to do this philosophy of having writing it as a driver for running a device, then what is this going to look like? All right, so here's the C# code for doing this. Oh, I have a little pause key here. What does that do? That hopefully will pause my slide. No, it doesn't. Okay, so this slide's going to certainly advance on me as all the others have. All right, so, yep. It will. It will? Ah, okay. All right, I will believe you. Let's hope that's the case. All right, good. So here we have a quantum random number generator, which all it's going to do is take a qubit, apply a Hadamard, measure it. So a 50-50 chance of seeing a 0 or 1 coming as the result. And this is the C# code that does that. Okay, so the very first line, result equals 0, seems a little bit odd. We'll get back to that a little bit later. But here we do exactly what we sort of expect to do, right? We get a qubit, we claim a qubit. Okay, then we apply a Hadamard gate to it, we measure the result, and then we have this reset thing down at the bottom, which it's not obvious what we're doing. Fine, but really perhaps the most interesting thing, and the thing that I'd like to stress, is we write Hadamard of qubit. I mean, we're familiar from that. If you're familiar with working in chasm of any variety, that's exactly what you would expect to see. But if you were writing in a functional programming language or something else, we'd see something more like in the comment line there, that the Hadamard acts on a qubit and gives me some result. Okay, but the picture that we have here is different. That's not really the view. The qubit isn't the state, so to speak, but rather it's a maybe reference to the state, or as really the way it's implemented, it's going to be an operation itself. Okay, and that's the view that we have to take if we're going to have this sort of device-centric view of things. Okay, so normally we would think of the input as being a state. I give the state 0 to our Hadamard gate, and out comes the plus state. But that's not the view. That's not the right view. Qubit is something that exists in this device, and so what we're just saying is, let this operation act on it, the device will do it. Okay, so qubit is something that has a state. It really isn't a state itself. Okay, so in fact, if I take that just a little bit more in a more sophisticated view, I could view qubit itself as an operation. It's the operation that takes the 0 state and gives me whatever state that it's referring to presently. Okay, so when I run my program, it's just, in some sense, the identity takes the 0 state to the 0 state. But as the program evolves, the qubit reference is referring to some operation that produces a qubit in whatever state is appropriate. So for instance, we might have these formulas on the left here where I apply a Hadamard, or maybe I apply a Hadamard in C0, and that would be the thing that would come out of my QKD program. But really, these elements are operations, or maybe programs, that start at a 0 state and then are in whatever state is appropriate for the device that's being driven. All right, so in particular, this view, since we're going to be passing around qubits, means that the operations themselves are the objects that we pass as values. Okay, so those are going to be our first-class entities in this programming language. Okay, so let's return to our picture here. Okay, so now focusing on the using command and the reset command, if these qubits aren't states, but rather they're operations from which are constructing states, well, then the first statement makes perfect sense. I'm going to build that operation. I'm going to build that program, if you will. But now the second one makes sense too, is I need to return that program to its original form in order to free the memory associated to it. So anytime we claim a qubit, we have to reset it to its state, And that has a number of nice side effects, if you will, is that we're not going to be destroying qubits and then hence creating unexpected effects. Everything has to be properly measured and deallocated as a result. Okay, so in particular, the very top statement now, the result equals 0, refers to the 0 program. Okay, so 0 is the program which takes the state 0 and leaves it in the state 0. Whereas if I had a 1 up there, it would be the program which takes the state 0 and prepares the state 1. And those are the things that we're setting equal to each other in the set result command. Okay, great. All right, so what is a program? Well, it's essentially exactly as we were expecting. We're going to do a computational task. We're going to have our quantum side effects, which we're then going to measure and utilize in our great program. But this principle of driving the quantum computer means that we really need to discuss the communication between the user and the device itself, and that's really what the language is trying to codify. And so really when we build an algorithm, we want to have the language help us understand what the algorithm is doing. Okay, and so in some senses it's really simple to take something like conjugation with a unitary, which appears in all kinds of algorithms, but we want the language itself to be able to convey that at a conceptual level rather than just a syntactic level. Okay, so I might say have the apply with command here, where I want to increment a phase, and so I conjugate an incrementer with the quantum Fourier transform, and that forms this operation, which is now a new operation, but we didn't have to really understand that it was this conjugation, but it's just transforming one frame into another frame. Okay. And so let's dig into that a little bit more, and let me do it by an example. Okay, so if I want to create this Bell pair, again, a very useful thing for our quantum key distribution experiment, we do a Hadamard on one of the qubits and then do a C0. Okay, now I didn't say C0 there. I'm using a controlled X for a very specific reason, because I'm highlighting that our conjugation that we did has some functorial properties, and those functorial properties can be carried through our construction. So for instance, if the U that I've done, the U dagger that I had on the previous slide wasn't QFT, but say EPR, I mean, that's a unitary operation. I can certainly take its adjoint. I don't know that it would be necessarily useful in this particular circumstance, but I can tag that this operation I'm constructing has an adjoint. Okay, and so if I tag it with the is adjoint, then the compiler itself understands how to construct the adjoint from this by inverting the order of the unitary operations in it and taking the adjoint of each of these. Controlled is another one of these functors. I know how to take an X gate, and since this can be, we can have controlled wires driving this X gate, we can use this functor and say construct controlled X. We don't have to build it ourselves. The compiler understands what to do. It can test the wires, in this case the array of wires called left, and control the X gate acting on the wire right. It knows what to do. Okay, so in this case there's only one wire, and so we don't need to give controlled any more information. Okay, so going back to our apply with command. Now, I guess there was I decided not to do apply with CA. CA is a little tag here, which says that this operation, which takes a type T, it is amenable to the controlled functor and the adjoint functor. Okay, so it's whenever building these things, building a compiler, it's sort of hard to decide what you're going to build into your syntax versus what you want to build into interpretation or semantics. Okay, so the operation of constructing this, I got the dagger on the wrong side, this U dagger VU is really built right here. And so this is the underlying C# code that is inside this library routine apply with CA, and it does exactly what you would expect. It's just going to compute the adjoint, then take the inner, and then take the outer. Okay, and I guess that's consistent. It's just not really consistent with what I had on the previous slides. Okay, so I'll just give everybody a chance to parse that. All right, so let me sort of finish this off by we can now express this as a very simple command in this using with, but really what we'd like to do is pull that even further apart and say, well, it's not really important that it was U, V, U dagger, and we already saw a little bit of this on the previous slide. The operations themselves are sort of irrelevant. What I want to do is have a type expression which allows me to put any type of operation in here, and that conjugation makes sense for whatever operations we'd like to have. Okay, this is a familiar object. So for instance, if I have a pair of things, this is just basic computer science. If I build a pair, then I have this operation, take the first element, and it doesn't really care what's inside of the pair. It doesn't make any difference because it knows what to do irrespective of that. And so the same sort of thing we can bring into the quantum regime, if you will, but now there's a little bit of a difference between the quantum types and classical types. So for instance, it's we understand what map does. If I have a function from type T to type U and I want to apply it to an array of elements of type T, then we all know what to do. We just apply this function to each of those in turn and produce an array of type U. Okay, and so here's a little piece of C# code that does that, and that's built into the intrinsics. But in the quantum case, operations are a little bit different. Okay, so quantum operations, we think of the Hadamard. Well, what's its type? Well, it's not of type qubit to qubit, which you might think would be the natural thing to do, because the quantum operation isn't actual operation, it's a side effect. Okay, so what does a Hadamard gate actually do in QuArC? Well, it takes a qubit and produces no output. Okay, it produces type unit because all of the quantum operations are happening on the side. Okay, so that changes the way we have to think about how we allow operations to act on our structures. So for instance, this is the analogous of the classical map. I want the operation T to apply to an array of qubits in this case, say. Then it runs on each one of these in turn as we have this loop here, but it doesn't return anything. And so it's all built into the side effect. It's happening in the quantum device or in the resource counter, but it's not returning anything to the classical driving program. Okay, so I am well on my way here to the end of time, and so let me finish up really quick. Here's an example from this view, the Grover's algorithm, very straightforward. Our qubits aren't really states per se, but they're operations, and we pass them as first-class citizens in the language. And so here we do the very straightforward reflect around a mark state, then reflect around the starting state or the equal superposition state. And so this quantum search is built right into the library, just pass the appropriate routines, and then one can run resource counting on it or whatnot. So this is all available as part of the samples. And so as I am out of time, let me finish. The Quantum Development Kit is open source. We're looking for contributions. The goal, of course, is to have a very, very rich library so that when you want to develop your quantum program, you don't have to rebuild simple things such as amplitude amplifications, Grover's search, et cetera, from scratch. Quantum phase estimation, for instance, it's all available to you, and you can focus on the more interesting parts of the program itself. All right, thank you.